Hello students, today we are going to discuss equilibrium of a rigid body, whether it is rotating about a fixed axis or it is at stationary. As we know, the torque is the rotational analog of the force acting upon a body, and the angular momentum of a rotating body is the rotational analog of linear momentum. If the net effect of the different torques or the different angular momentum of the body is such that the resultant of angular momentum and the resultant of torque is 0, means their vector sum is 0. In that case, the body will be in equilibrium. But it does not mean that the torque is not acting there. Individual torques are acting there, individual angular momentum are acting there, but the net angular momentum and the net torque acting on that object or rigid body is 0. That's why it is in equilibrium condition. A rigid body is in mechanical equilibrium if both linear and angular momentum of body are constant with respect to time. Means there is no change in linear momentum of the body and angular momentum of body. Then the rigid body is in mechanical equilibrium. It also contributes that if both linear and angular momentum of body are constant, there will be no linear acceleration and no angular acceleration of the body. In that case, the net force acting on that rigid body is balanced. Similarly, the net torque acting on the body is balanced. So it means that no angular or linear acceleration is being provided to the body. That means the net external force on body is 0. The vector sum of all the forces acting on that body is 0, and net external torque on body is also 0. So it is clear, if the total vector sum of torque acting on that body is 0, it means there is no angular acceleration in that body. And if the net force or the vector sum of all the forces is 0, then the net linear acceleration of the body is not there. It means if on the same body the coplanar or non-coplanar forces or torques are acting there, and if the vector sum of all the forces and torques are 0, the body will be in mechanical equilibrium. So the forces may be coplanar or non-coplanar, but they must be concurrent to provide the situation that the resultant effect of force or torque is 0 when the linear or angular acceleration of body will be 0, and thus the body will be in mechanical equilibrium. A body may be in partial equilibrium also. It means it may have an angular acceleration but may not have linear acceleration. Similarly, a body can have the linear acceleration but cannot have the angular acceleration. We can take such an example for each. A rigid body in partial equilibrium. Let us consider the first case. The body may be in translatory equilibrium. That means linear acceleration is zero and it will not be in rotational equilibrium. For example, consider a situation where a rod of light mass, the rod AB, shown in the figure in red color, is balanced initially on a peg shown by yellow color. The peg is supporting that rod at its center of mass. So initially the rod is balanced. Now, if a force acts at its one end A downwards and another force with the same magnitude act at its other end upwards, in that case, since the both of the forces have same magnitude but are in opposite direction, then the net resultant force acting on that rod will be zero. But still you can see the body will not be in rotational equilibrium because the force acting on both ends of the rod A and B will try to rotate the rod with respect to its center of mass in anticlockwise direction. That means the moment of the force applied at the ends of the rod will try to produce its rotation with respect to the axis of passing through its center of mass such that it can rotate in anticlockwise rotation. So in this case, the rod AB is in translatory equilibrium since F net acting on that body is zero. But the rod is not in rotational equilibrium. The net torque on the rod is not zero. And it is clear the equilibrium condition of the rod is being discussed here with respect to its center of mass where it is supported on a peg. So, in the non-equilibrium condition of the rotational torque, it will try or tend to rotate in anti-clockwise direction. Or you can say it will lift from the end B to upward and it will go down from the end A downward. Let us take the second case. The body may be in rotational equilibrium but may not be in translatory equilibrium. Let us consider the same example of the rod. Again the same light rod is placed on the peg at its center of mass, so it is balanced, and now the two forces are acting at its two ends having the same magnitude and having the same direction of action. In that case, the net rotational motion is not there for the rod because the forces are balanced with respect to the axis of rotation passing through the center of mass of the rod. So the rod will not try to move or to rotate either in clockwise or in anti-clockwise rotation. But there is net force acting on the rod in the downward direction. Since the force at its one end A is acting downward, and also the force at its another end B is acting downwards. So the net vector sum of the forces is not zero, but the rotational analog of force is zero. It means in this situation, the rod is in rotational equilibrium but not in translatory equilibrium. But the rod is not in translatory equilibrium. The net force on the rod is acting there in the downward direction. So I think it is clear to you that the body may be in both translatory or rotatory equilibrium, or maybe in partial equilibrium where the translatory equilibrium will exist but not the rotatory equilibrium, or the rotational equilibrium will exist for the body but not the translatory equilibrium. So we have discussed the two cases. That's all for today. Thank you.